In this video, I will use the theory that I went over for accelerating but not rotating frames of reference, and I will use this theory to explain the phenomenon that we see with tides. So what I have here is the moon, this is the earth. I have my coordinate system, my frame of reference, the origin of the coordinate system is here, the center of the planet, x, y. I'm considering a mass, the lowercase m. Let's use uppercase M sub E for the mass of the earth and uppercase M sub M for the mass of the moon. And I have some mass here. Now I'm not going to specify what this is. You can think of it of anything you want. But in the application to tides, this will simply be if you want a bucket of water or a water drop, something, a part of the water that we have in the sea, in the ocean. And I'm showing the different position vectors. So the R naught is the position vector of this mass with respect to the moon. Uppercase R is the position vector of the center of the earth with respect to the moon. And then I have the lowercase r, the position of the mass with respect to the earth. Now, this is the theory we got from our previous work. And one thing that I want to do to show you how you can work on the net force. So this is my system, this is the mass. And I know that it has some interactions with the surroundings. What are those interactions? There is a gravitational interaction between the mass and the moon. Okay, so this is what the lowercase g stands for. And there is a gravitational interaction between the mass and the earth. This is what this describes. But also, we do consider the possibility that there are other objects interacting, say via a contact interaction, that's why I have the C, with our system, the mass. Now, even if this interaction is not contact in nature, but it is electric, magnetic, whatever, it doesn't matter. Okay, at the end of the day, what I want to show you here is that there may be other things in addition to the moon and the earth interacting with our system. And if that is the case, then we have to take it into account in our net force calculation. So for this system, the mass, using the interactions, I would say the net force is the gravitational force from the moon to the mass plus the gravitational force from the earth on the mass plus, in this case, I'm just going to do contact from other stuff to the mass. Okay, so based on the interactions, I will have three forces. Now I can write minus g lowercase m sub e, the magnitude of r squared times r hat. Now this is okay, hold on. So I started working on the one from the earth instead of the one from the moon. So this is going to be minus g lowercase m, the mass of the moon. This is going to be the distance r naught squared, r naught hat, the unit vector. And then I have the one from the earth, minus g lowercase m, the mass of the earth, the magnitude of r squared times r hat. Now, okay, the mass for the gravitational force from the mass from the moon to the mass, I do need to use this expression. Now, for the one from the earth, assuming that this mass is fairly close to the planet, it's not necessary that you use this. Okay, we saw in introductory physics, if you have an object near the surface of the planet, you can just do m times the lowercase g, and the lowercase g, let me show you here. So this is what the lowercase g stands for. So if the object is near the surface of the planet, you can just do mg times r hat for the direction. But if it is not that close to the planet, then you have to do this. And then we have, of course, the rest. Any other forces that are taking place. Now, with this, let's call this equation 1. This is my equation 2. With this, I've taken care of this term. Now I'm going to take care of the acceleration. This is the acceleration of the Earth, the planet, with respect to the moon. And this acceleration is due to the fact that the moon exerts a force, a gravitational force on the Earth. And this force, so the magnitude of the gravitational force that the moon exerts on the Earth is equal to g, the mass of the moon, the mass of the Earth, divided by their distance squared. Now, remember, I'm looking for the acceleration of the Earth. So I can say the acceleration caused by this force on the Earth will be equal to this. Now, let's do the following. Let's not use the magnitude. Let's go and include the directions here. So this is, knowing the direction, just going to make my life easier afterwards. So this is going to be minus and then r hat. And then this is equal to the mass of the Earth times the acceleration caused by this gravitational force. Now, because I have the mass of the Earth on both sides, this allows me to say this acceleration caused by the gravitational force of the moon on the Earth is minus g, the mass of the moon, divided by r, the magnitude of r squared, times r hat. And now that I have everything, I can plug in everything to equation 1. So using equation 2, using equation 3, this is going to give me, I'm going to start from here since I'm going to have quite some things, minus g lowercase m, the mass of the moon. I'm just copying what I had from my other equations, r naught hat minus mg r hat. Okay, I'm making my life a little bit easier by not writing all of this. Lowercase g, I'm assuming it is close, the object is close to the surface of the planet, plus any other forces acting on the system. And then I have minus the mass times the acceleration that I found. Alright, and this becomes mr double dot. I will change the order now. I will have the gravitational force from the Earth first. I will have any other forces acting on the mass second. And then because this, the first term and the last term include g and m and the mass of the moon, I will write them here. So I got minus gm, the mass of the moon, and then what is left will be r naught hat over are the magnitude of that distance squared. And then I have minus r, big R hat, over the magnitude of the big R squared. Now, this is the gravitational force from the Earth on the mass. These are some other forces. And this term includes two things. One is the gravitational force from the moon, but there is also a component that is due to the fact the Earth is not an inertial frame of reference. Now, to see how this term affects the tides, we have to compare. We need to find the direction. Okay, this is a vector. We need to find the direction of this for different locations. The first one, you can say if the mass m is somewhere here. If the mass is somewhere here, then the distance from the moon to the mass, meaning this number, is going to be smaller than this distance. And that means, because the magnitude of the unit vectors are both 1, this means that this term will have a greater influence when the mass is here, and with a minus sign you will have a direction for this term that goes to the left. And this direction, this explains why you have a large tide on this side of the planet. Okay, it is not just due to the fact that the moon is exerting a force on the ocean. It's also due to the motion of the planet, the acceleration of the planet around the moon. Now, on the other hand, if you have the mass m and you move it on the other side, then this is going to be greater than that, and this term will have a greater influence when you add these two together. So with the minus sign and the minus sign, you end up having a positive direction, a positive r hat direction. So for a mass m that is here, this vector quantity points in this direction, and this explains the high tides, the large tides that you have on this side of the planet.